Hello, this is my English speaking practice, and I'm talking about my tech study. And today I'm going to study about. I'm wondering which to study. OS, operating system, and writing an OS in Rust. Okay. Yeah. So let's create. No. Today it's September 1st, so I was wrong yesterday's date. Okay, so this blog series creates a small operating system in the Rust programming language. Each post is a small tutorial and includes all needed code so you can follow along if you like. The source code is also available in the corresponding GitHub repository, and yeah, there are some articles about features in OS, and I what should I start with? Pacing, memory management is a important topic. Interrupts is close to hardware layer. Bare bones. I'm not sure. The first step in creating our own operating system kernel is to create a Rust executable that doesn't not link the standard library. This makes it possible to run Rust code on the bare metal without an underlying operating system. That makes sense. Bare metal. So there is no operating system. I see. In information technology, bare metal is a computer which has no operating system. Yeah. So AWS is to bare metal. Yeah. AWS provides bare metal instances. Amazon EC2 metal instances provide you with physical CPU, not virtualized CPUs. Metal instances are not virtualized, they do not run under hypervisor like non-metal instances do. Yeah, we do use the same vCPU terminology in our APIs and the EC2 console even with metal instances, but rest assured you will have full access to all CPU resources. Okay, just a point of clarity, EC2 dedicated hosts are different from metal instances. EC2 dedicated hosts are intended to run multiple EC2 instances on the same physical machine. So the question is, what is the question? I would like to create a user bare metal instance with GPUs. The documentation states that I have to go to EC2 and create a dedicated host by choosing an instance such as M5, for example. My problem is that when I create a dedicated host, the interface shows me vCPUs, which I don't understand. Normally, if my instance is bare metal, I should have real physical CPUs and not vCPUs. So I'd like to know if this is a real procedure for accessing a bare metal host and on with GPUs. Oh, I see. Okay, I understand bare metal, but I'm not sure how to run the program code on without operating system, because I haven't tried it, haven't used bare metal, so I cannot imagine the situation or usage or like that. But let me read this article. The first step in creating our own operating system kernel is to create a Rust executable that doesn't link the standard library. This makes it possible to run Rust code on the bare metal without an underlying operating system. This blog is openly developed on GitHub. If you have any problems or questions, please open an issue there. You can also leave comment at the bottom. The complete source code for this post can be found in the post01 branch. To write an operating system kernel, we need code that does not depend on any operating system features. Yeah, that makes sense. This means that you cannot use these threads, files, heap memory, the network, random numbers, standard output, or any other features requiring OS abstractions or specific hardware, which makes sense since we are trying to write our own OS and our own drivers. This means that we can't use most of the Rust standard library, but there are a lot of Rust features that we can use. For example, we can use iterators, closures, paramarketing, option and result, string formatting, and of course the ownership system. These features make it possible to write a kernel in a very expressive, high-level way without worrying about undefined behavior or memory safety. In order to create an OS kernel in Rust, we need to create an executable that can be run without an underlying operating system. Such an executable is often called a freestanding or bare metal executable. This post describes the necessary steps to create a freestanding Rust binary and explains why the steps are needed. If you are just interested in a minimum example, you can jump to the summary. A minimum freestanding Rust binary looks like this. No standard and no main. Don't link the Rust standard library, and disable all Rust level entry points. Don't mangle the name of this function. Mangle can refer to a verb meaning to severely damage, destroy, or spoil. Severely damage. To destroy or injure. Unsafe no mango. This function is the entry point since the linker looks for a function named underscore start by default. This function is called onPanic. Okay. And this is a cargo. So this is about the build profile or like that. The profile used for cargo build. Disable stack unwinding onPanic. File used for cargo build release. To build this binary, we need to compile for bare metal targets such as ThumbV7EM. Alternatively, we can compile it for the host system by passing additional linker arguments. Note that this is just a minimum example of a freestanding Rust binary. This binary expects various things. For example, that the stack is initialized when a start function is called. Go back to here. Disable the standard library. Okay. Okay. So by default, yeah, it uses OS features and uses libc, which closely interact with OS services. So need to disable the standard library and we start by creating a new cargo application project. The easiest way to do is through the command line like this. Okay. No standard attribute. Yeah. println macro is part of the standard library, so which we no longer include so we can no longer print things. This makes sense since println writes to standard output, which is a special file descriptor provided by operating system. So let's remove the printing and try again with an empty main function. Now the compiler is missing a panic handler function and a language item. The panic handler attribute defines the function that the compiler should invoke when a panic occurs. The standard library provides this own panic handler function, but in no standard output environment, we need to define it ourselves. Okay. What is this? Language items are special functions and types that are required internally by the compiler. For example, the copy tolerate is a language item that tells the compiler which types have copy semantics. when we look at the implementation, we see it has the special lang equals copy attribute that defines it as a language item. Language item. So while providing custom implementations of language items is possible, it should only be done at the last resort. The reason is that language items are highly unstable implementation details and not even type checked. So the compiler doesn't even check if a function has the right argument types. Fortunately, there is a more stable way to fix the above language item error. The EH personality language item marks a function that is used for implementing stack unwinding. Stack unwinding. Stack unwinding. Adding a subroutines entry to the core stack is sometimes called winding. Conversely, removing entries is called unwinding. Okay. Stacks are last in, first out data structures. In other words, the last item pushed on the stack is the first item popped from it. To understand how C++ performs function calls, we should know it's using a stack data structure. The function call stack supports the function call return mechanisms. It also supports the creation, maintenance, and destruction of each called function's automatic variables. This LIFO behavior is exactly what a function does when returning to the function that called it. Since the call stack is organized as a stack, the caller pushes the return address onto the stack, and the called function, when it finishes, pops the return addresses of the call stack and transfers control to that address. Okay. If a called function calls onto yet another function, it will push another return address onto the call stack, and so on, with the information stacking up and unstacking as the program dictates. Program dictates. So we must keep track of the return addresses that each function needs to return control to its caller. The function call stack is the perfect data structure for handling this information. Each time a function is called, an entry is pushed onto the stack. This entry, called the stack frame, activation frame, or an activation record, contains the return address that the called function needs to return to the calling function. When the called function returns, the stack frame for the function called is popped, and control transfers to the return address in the popped stack frame. Each called function always finds the information it needs to return to its caller at the top of the call stack, and if a function makes a call to another function, a stack frame for the new function call is simply pushed onto the call stack. Thus, the return address required by the newly called function to return to its caller is now located at the top of the stack. So, removing entries is called unwinding. Okay. Okay. By default, Rust uses unwinding to run the destructors of all live stack variables in case of a panic. This ensures that all used memory is freed and allows the parent threads to catch the panic and continue execution. Unwinding, however, is a complicated process and requires some OS-specific libraries. So we don't want to use it for our operating system. Disabling unwinding. There are other use cases as well for which unwinding is undesirable. Undesirable. So Rust provides an option to abort on panic instead. This disables the generation of unwinding symbol information and thus considerably reduces binary size. There are multiple places where we can disable unwinding. The easiest way is to add the following lines to our Cactomo. I will skip here and I want to know about how to run it on bare metal. By default, Rust tries to build an executable that is able to run in your current system environment. For example, if you are using Windows on x86-64, Rust tries to build an Windows executable that uses x86-64 instructions. And this environment is called your host system. To describe different environments, Rust uses a string called target tuple. you can see the target triple for your host system by running rustc version values. The above output is from x86-64 Linux system. We see that the host triple is which includes the CPU architecture, the vendor, the operating system, and the ABI. By comparing for our host triple, the Rust compiler and the linker assume that there is an underlying operating system such as Linux or Windows that uses a C runtime by default, which causes the linker errors. So to avoid the linker errors, we can compile for a different environment with no underlying operating system. An example of such a bare metal environment is the target triple, which describes an embedded ARM system. The details are not important. All that matters is that the target triple has no underlying operating system, which is indicated by the none here. Now, in the target triples, to be able to compile for this target, we need to add it in Rastrap. Rastrap target add none. This downloads a copy of standard library for the system. Now we can build our freestanding executable for this target. By passing a target argument, we compile our executable for bare metal target system. Since the target system has no operating system, the linker doesn't try to link the C runtime, and our build succeeds without any linker errors. This is the approach that we will use for building our OS kernel. Instead of we will use a custom target that describes the x86-64 bare metal environment. The details will be explained in the next post. I understand that when I create a operating system in Rust language, I will use the bare metal instance that doesn't have an operating system, and I need to set up the environment or build systems, build settings. So it needed to not to use the standard libraries or linkers or like that. Yeah, I understand that, but I don't know. I don't know how to run it. Yeah, I understand. I can choose the build target and specify the none as a operating system. That makes sense, but I don't know. After compile it, I can get the executable on the bare metal, but I don't know how the interface on bare metal instance can get a command line interface, but it's a shell, so it's a one of features operating system. So that's my question. Bare metal means there is no operating system to run your program. You have a few options. Emulator. Most tutorials boot the Rust kernel inside a queue. Oh, this emulates hardware, so your OS runs without. Okay. Real hardware. You need a bootloader. The bootloader loads your Rust kernel into memory and jumps to it. You then flash it. Okay. So the ChatGPT mentioned about the VGA text buffer. VGA text mode is a simple way to print text to the screen. In this post, we create an interface that makes its usage safe and simple by encapsulating all unsafety in us. We also implement support for Rust format macros. How about this? QEMU. We can now boot the disk image in a virtual machine. To boot it in QEMU, execute the following command. So QEMU is a hardware emulator, a generic and open source machine emulator and virtualizer. Okay. So I should read this article maybe. To make it clear. In this post, we create a minimum 64-bit Rust kernel for the x86 architecture. We build upon the freestanding Rust binary from the previous post to create a bootable disk image that prints something to the screen. Oh, really? Where have we implemented the print something features, printing features. Print. To create a bootable disk image. So we don't have printing features yet. Okay. The boot process. When you turn on the computer, it begins executable firmware code that is stored in motherboard ROM. This code performs a power-on self-test, detects available RAM, and pre-initializes the CPU and hardware. Afterwards, it looks for a bootable disk and starts booting the operating system kernel. On x86, there are two firmware standards. The basic input-output system called BIOS and the newer Unified Extensible Firmware Interface UEFI. The BIOS standard is old and outdated, but simple and well supported on any x86 machine since the 1980s. UEFI, in contrast, is more modern and has much more features, but is more complex to set up, at least in my opinion. Currently, we only provide BIOS support, but support for UEFI is planned too. If you'd like to help us with this, check out the GitHub issue. BIOS boot. Almost all x86 systems have support for BIOS booting, including newer UEFI-based machines that use an emulated BIOS. This is great because you can use the same boot logic across all machines from the last century. But this wide compatibility is at the same time the biggest disadvantage of BIOS booting because it means that the CPU is put into a 16-bit compatibility mode called real mode before booting, so that archaic bootloaders from the 1980s would still work. I've heard of this real mode. CPU is put into a 16-bit compatibility mode, real mode. Real mode, also called real address mode, is an operating mode of all x86 compatible CPUs. The mode gets its name from the fact that addresses in real mode always correspond to real locations in memory. Real mode is characterized by a 20-bit segmented memory address space. 20-bit segmented memory address space, giving 1 megabyte of addressable memory and unlimited direct software access to all addressable memory. Real mode provides no support for memory protection, multitasking, or code privilege levels. Before the introduction of protected mode with the release of processor's name. Real mode was the only available mode. And backward compatibility, all x86 CPUs start in real mode when reset. Though it is possible to emulate real mode on other systems. Let's start from the beginning. Oh. Okay, I will skip. But I think this part is important. This is about boot process, so I will read here. When you turn on computer, it loads the BIOS from some special flash memory located on the motherboard. The BIOS runs self-test and initialization routines on the hardware. Then it looks for bootable disks. If it finds one, control is transferred to its bootloader, which is a 512-byte portion of executable code stored at the disk's beginning. Most bootloaders are larger than 512 bytes, so bootloaders are commonly split into a small first stage, which fits into 512 bytes, and a second stage, which is subsequently loaded by the first stage. The bootloader has to determine the location of the kernel image on the disk and load it into memory. It also needs to switch the CPU from the 16-bit real mode first to the 32-bit protected mode, and then to the 64-bit long mode, where 64-bit registers and complete main memory are available. Its third job is to query certain information, such as a memory map, from the BIOS and pass it to the OS kernel. Writing a bootloader is a bit cumbersome. Cumbersome is an adjective describing something that is large, heavy, and thus difficult to carry, handle, or use. Okay, writing a bootloader is a bit cumbersome. So heavy task, as it requires assembly language and a lot of non-insightful steps like write this magic value to this processor register. Therefore, we don't cover bootloader creation in this post, and instead provide a tool named boot image that automatically prepends a bootloader to your kernel. If you are interested in building your own bootloader, stay tuned. A set of posts on this topic is already planned. Okay. The multi-boot standard. I don't need to read this part. And for I don't need to know about the Rust features, so I will go to here. Now that you have an executable that does something perceptible, it's time to run it. First, we need to turn our compiled kernel into a bootable disk image by linking it with a bootloader. Then we can run the disk image in the cube virtual machine or boot it on the real hardware using a USB stick. So we write the code like this and compile it and get the executable. Okay, executable means it is a disk image, bootable disk image. We need to turn our compiled kernel into a bootable disk image. And then we can run the disk image in the Cube virtual machine. I see. So we haven't created a boot image, just compiled. Okay. So how to create a boot image? To turn our compiled kernel into a bootable disk image, we need to link it with a bootloader. As we learned in the section about booting, the bootloader is responsible for initializing the CPU and loading our kernel. Instead of writing our own bootloader, which is a project on its own, we use the bootloader crates. This crate implements a basic BIOS bootloader without any C dependencies, just Rust and inline assembly. To use it for booting our kernel, we need to add a dependency on it, like this. Adding the bootloader as a dependency is not enough to actually create a bootable disk image. The problem is that we need to link our kernel with the bootloader after compilation, but Cargo has no support for post-build scripts. To solve this problem, we create a tool named bootimage that first compiles the kernel and bootloader, and then links them together to create a bootable disk image. To install the tool, go into your home directory and execute the following command in your terminal. So this tool is created by the author of this post. For running boot image and building the bootloader, we need to have the LLVM tools preview Rust app component installed. You can do so by executing the Rust app component at LLVM tools preview. After installing boot image and adding the LLVM tool preview component, you can create a bootable disk image by going back into your Cargo project directory and executing. Cargo boot image. We see that the tool recompiles our kernel using card build. so it will automatically pick up any changes you make. Afterwards, it compiles bootloader, which might take a while. Like all create dependencies, it is only built once and then cached, so subsequent builds will be much faster. Finally, boot image combines the bootloader and your kernel into a bootable disk image. After executing the command, you should see a bootable disk image named boot image dash blog OS bin in your target debug directory. You can boot it in a virtual machine or copy it to a USB drive to boot it on real hardware. Now note that this is not a CD image, which has no different format, so burning it to a CD compact disc doesn't work. I see. I have created a boot image at work. And also I've burned it to the CD. But that is a CD image. I have experienced that I've installed the Ubuntu boot image into USB. Yeah. Okay, so in this case, the Ubuntu is replaced once that we create a minimum kernel, right? Okay, makes sense to me. And how does it work? The boot image tool performs the following steps behind the scenes. It compiles our kernel to ELF file, executable linked file format, executable and linkable format. File format for executable files: object code, shared libraries, core dumps. Object code, core dumps. Elf Linux executable workthrough. Header mapping execution. Header sections, header loading process. Okay. So create a elf file and it compiles the bootloader dependencies as a standalone executable. And it links the bytes of the kernel elf file to the bootloader. So elf file is linkable, so it links the bytes of the kernel elf file to the bootloader. When booted, the bootloader reads and parses appended L file. It then maps the program segments to the virtual addresses in the page tables, zeros, the PSS section, and setup. Finally, it reads the entry point of our address. 50% understand. So anyway, we've create a boot image. That means compare the Rust source code to a kernel, compare the kernel, and this tool make it Elf file and also linked it to the bootloader. I don't know, bootloader is a so this case they don't write the bootloader. Bootloader create, and this create implements a basic BIOS bootloader without any C dependencies. So that means the bootloader is also Rust module, and so bootloader is also installed in Rust side, and use this tool and compare the bootloader dependency as a standalone executable. Okay. And booting it in Qum, we can now put the disk image in virtual machine. To boot it in Qum, execute the following commands: Qum system drive format file target boot image. So this file is bootloader, right? No, boot image. Boot image. Bootable disk image. Yeah. So this is a bootable disk image that links to bootloader in my understanding. And it is also possible to write it to a USB stick and boot it on the real machine, but be careful to choose the correct device name because everything on that device is override. VGA text mode. In this post, we learned about the structure of the VGA text buffer and how it can be written through the memory mapping address. We created a Rust module that encapsulates the unsafety of writing to this memory mapped buffer and prevents a convenient interface. Thanks to Cargo, we also saw how easy it is to add dependencies on third-party libraries. The two dependencies that we added, lazy static and spin, are very useful in OS development, and we will use them in more places in the future post. Okay. So in this post, there is no OS features, so but it can use the Rust crates as far as it doesn't use these Rust OS features. So this is not a standard output. This is another way to print text to the screen. Yeah. So from this post, they started to create a kernel. Kernel features. Okay. And testing. Requirements testing existing queue. CPU exceptions. Okay, this is a bare bones. I've learned a lot. So I want to speech about what I've learned today. I've learned now. Let me try. I'm gonna talk about what I've learned today. I've learned OS development in Rust and how to start it. Yeah, I couldn't imagine how to start the program without operating system. Yeah, but I understand it. Yeah, so in the Filippo Opperman's blog, it uses the QEMU Cube. That is the hardware emulator. So all we have to create is a boot image, and yeah, with Cube, we just provide the boot image as an argument. Okay, so the goal is to create a boot image. Why do you translate into Japanese? Today I'd like to talk about operating system development. At first I couldn't imagine how to develop a program without using existing OS, but now I understand it. In Philip Opperman's blog, he uses Qum, which is a hardware emulator, to run your own OS. You need to create a boot image. Then you can pass that boot image as an argument to Qum. Pass that boot image as an argument to Qum, and it will boot your system. Oh. Please don't translate this into Japanese. You just print it as original English. Yeah. And today, let me continue to explain what I've learned. So, to create a bootable disk image, they uses the Rust crate. Yeah, that can compile the bootloader and create a ELF file, executable and linkable format file. So yeah, that was easy. So that regarding for source code, it is very simple. It just print not print, I don't know, but it doesn't have any features. Yeah, and also it needed to flag as no standard because there is no operating system. So yeah, it needed to specify, it needed to declare no use of standard libraries. Okay. Yeah. But that's it. That's it. So that's it. And compile it as a minimum kernel, and the boot boot image, or there is some tool and that can compile it and convert it into ELF format, and also install the bootloader as a dependencies, and it can link the ELF to bootloader. Yeah, so the tool can do that. And that's it. And we can get a bootable disk image. But to be honest, I don't know the ELF file and bootloader is one is a put together, or it is they are separated, or I don't know about that. But they can get a bootable disk image, and they pass it as an argument to queue. Okay, I will do I will do a short talk. So to create a bootable disk image, they uses a tool. Yeah, the tool can compile the kernel and convert it to the ELF file, and also install the bootloader dependencies. Yeah. So and finally they link the ELF file and link ELF file to the bootloader. Yeah, that's it. So they get a bootable disk image. To create a bootable disk image, we use a tool. This tool compiles the kernel and produces the ELF file, and it also installs the dependencies needed. It also installs the dependencies needed for. To create a bootable disk image, we use a tool. This tool compiles the kernel and produces an ELF file. It also installs the dependencies needed for. This sentence is so easy. And to create a bootable disk image, we use a tool. This tool compiles the kernel and produces a Elf file. It also installs the dependencies needed for the dependencies needed for the bootable disk. Then it links the Elf file with the bootloader. Finally, we get boot. Okay. That's it. At last, I'd like to ask questions. Ask for questions. No. Ask for bootable disk image. Can I ask for bootable disk image? I've learned the Elf file linked to bootloader, but I don't know which is the bootable disk image. So they are separated, or they are as one image, and that is the bootable disk image. Yeah. Please explain it. Cannot recognized. I have a question. I've learned bootable disk image. Disk image. And they compile the kernel and produce a Elf file, and also that is linked to bootloader. So my question is, they are separated or they are as one file? And is that bootable disk image? I have a question. I've learned that they compile the kernel and produces a ELF file. Is that disk image? Or they are linked with the bootloader, so the ELF file linked bootloader is one file, and that is called bootable disk image, or not? Kernel compilation. When you compile your kernel in Rust, the compiler produces the ELF file as a standard binary format. It contains your machine code section, symbols, etc. But an ELF file cannot boot by itself on bare metal. PCs don't know how to load it. Bootloader, that's where the bootloader comes in. Yeah, the bootloader runs first. BIOS loads it. The bootloader knows how to load your kernel ELF into memory and start executing it. In the Rust ecosystem, people often use the bootloader crates. Disk image is a file that represents the contents of a bootable disk. It usually contains the bootloader host sector for BIOS or ELF executable for ELF and your kernel ELF, possibly bundled or linked into the bootloader. So the disk image is not the same as the ELF file. Instead, bootloader and kernel ELF. When you people say the bootloader and ELF are linked, it usually means the bootloader package takes your kernel ELF and embedded it into the bootloader, producing a single bootable bin or image file. That final file, the boot. So to answer your question directly, ELF, just your kernel program, bootloader and ELF combined, bootable file, disk image. Combined. So when you link the bootloader and ELF, the disk image is generated. A tool such as boot image will take the bootloader binary, embed it or attach your kernel. Produce a single file usually like this. Okay, so so let me wrap it up. We needed to write a code for kernel and without using standard libraries, and to create a bootable disk image we will use the tool such as boot image. That compiles the kernel and convert it ELF file, and also install the bootloader as a dependencies, and they can embed it or attach the kernel to bootloader, and at the same time produce a single file that is called a bootable disk image. That's it. To wrap up, I needed to write a kernel without standard libraries. Then to create a bootable disk image, I used a tool like boot image. This tool compiles the kernel and produces an ELF file, install the bootloader as a dependency, and attach the kernel to the bootloader. Finally, it outputs a single bootable disk image that I can run in Cube and Flash to use. That's it. Alright, to finish up, I'm writing the kernel with no standard. I use boot image to build it. It gives me an ELF file for the kernel, pull the bootloader, and bundle them together. The result is one bootable image I can run in Cube or real hardware. Done. This sentence is close to me. Close to mine. Install the bootloader as a dependency. Attach the kernel to the bootloader. It outputs a single bootable disk image that I can run in Cube or Flash to a USB. That's all. Hmm. Okay. Okay. Hmm. Hmm. I've been learn. Hmm? I've learned a lot. Hmm. So it's time to finish.